Okay, now we're into a very, very critical part of this probability and statistics related things that you probably almost certainly will, if you go on to be a serious structural engineer, for example, that you will actually use. And it's actually related to measuring things. So, for example, say you've got some kind of a structure, say a very old bridge structure, and you want to find out how strong the concrete is. Presumably concrete reduces in strength over the years. Now, if you want to measure the strength of the concrete, you have to actually take samples out, which in itself actually weakens the bridge, so you can't take so many. So suppose you can only take 6 samples out of the bridge, and you can go off and measure the strength of that concrete, and you can take the average strength and say, oh, this is how strong the concrete in the bridge is. But the question is, how accurate is that measurement? Essentially, that's what sampling theory here boils down to. You can't measure all of it, you just measure some, and how accurate is that is essentially the thing. So we'll talk about another average here. So consider the problem of finding the mean average length of all the metallic rods produced in a factory. Now we're imagining that all things are kind of staying the same, but this factory is producing millions of them. I want to find the average of all of them, because we want to, if we produce these metallic rods, we want to say, oh, the average length is 2 meters or whatever. It's impossible, to find the average length of all of them. But what you could do is approximate the population mean average, the average of all the possible rods that will ever be produced, by taking a random sample. Now, it's very important that you take a random sample. If, for example, you wanted to find out what proportion of CIT students smoked, and you wanted to look at 30 students, you couldn't just look at CE and EE3. That's not a random sample. All of the theory in this section is based on taking a random sample, which isn't as easy as it sounds. And I think it'll probably be something that is going to come into your assignment somehow. So what you do is you take a random sample. The general process is called sampling and is used to make inferences of it. Now, inferences is just making statements about the whole population just by looking at some of them. Like you want to make a statement about the average or the strength of the concrete in a bridge by looking at just some of the concrete. So suppose we measure the rods to have, say, these different lengths. And then what you can do is you can find the mean average of these. And this is called the sample mean. So add up all the lengths and divide by the number of numbers. So this is called the sample mean. So there's theoretically, say, infinitely many rods, and you take 100 of them. Find the length of all those rods, and find the average length. That's your sample mean. Now you can take the sample mean as an estimate of the population mean. Okay, so how accurate is this? So the thing is to consider all possible samples you could have taken from the population. So the population, usually you'll kind of say that there's n, so there'll be a smaller number like 100, and then the population is n, which is a large number, which could be theoretically millions, could theoretically be infinite. So there are many, many ways of choosing n rods from a population of perhaps millions. In particular, there are big N, choose N. This is something, will we see this? Maybe we won't. So big N, CN on your calculator. So if we'll do an example of one of those, suppose you've got a sample of 1,000, a population of 1,000, and you wanted to look at how many ways could you choose a sample of size 10. Big number. There's loads of samples. I don't know. Oh yeah, so here we go. So 1,000, choose 10 is approximately 10 to the 23. So there's loads of possible ways. So I'm saying there's 1,000 rods. How many ways can you pick 10 of them? How many samples are there? There's loads of them. So there's many, many ways of choosing n rods from a population of perhaps millions. If we look at the sample mean average as a random variable, then the mean average of the sample mean averages is equal to the population mean average. So what I'm saying is here, say in this scenario, we'll take this scenario here. There are 10 to the 23 possible samples, and let's kind of we'll call them, say, 1 to 20, 10 to the 23. There's loads of them, And let's look at the average of those. So there's 1,000 rods. You take 10 of them, you get the average. So the first sample, you get an average of whatever, 2.01. So that would be the first sample mean. And the second sample mean of a different sample. I don't know how you'd even number the samples. Third sample mean, fourth sample mean, all the way up to this 1,000 choose 10 sampling. So these are loads of different numbers. So if you think of this as a random variable, so before you take the sample, you don't know which sample you're going to get, and so you don't know what sample mean you're going to get. So there's chances that maybe by accident, like because it's random, there's a chance you pick the 10 longest rods, in which case you get a very, very large sample mean. Or similarly, there's a chance you somehow pick 10 the 10 shortest rods, and you get a very, very small sample mean. But actually, on average, most of them will be close to the population mean, which is mu. So this will give you an L bar. And the thing is, you think of this as a random variable itself, and the question is, what is the average of these? Okay, I think we are going to illustrate this on the next page because it's an important concept to understand. So each random sample has a sample mean. So the sample mean is a random variable itself. So before you take the sample, you don't know what you're going to get for the sample mean. It turns out that the average of the sample means is equal to the population mean. So the average of all of these, so if you look at all the possible samples of size 10, calculate the average of each of them separately, and then find the average of all these, you'll get the average of all the rods. Basically, the way it works is that every rod appears in an equal number of samples. That's basically the idea. So it turns out that the average of the sample means is equal to the population mean. You can show that the standard deviation, a measure of the spread of the sample means from the population, is given by this. So this sigma is how spread out the population is, divided by the square root of n, where n is the sample size. And we'll talk about that now in a second. So this says how spread out these sample means are. So yeah, we'll get into that. So these two factors, how spread out the population is and how large the sample mean, they influence the accuracy of this approximation. So you want to take a sample, get the average of the sample, and say that's what you think the population mean is. But these two factors influence how accurate that approximation is. Okay, so the first way you can make this more accurate, well, the only way you can make it more accurate, is let's look at this sigma over root n. Now sigma is how spread out the data is. So for example, if the rods are produced very shoddily, there's going to be lots of especially long rods, lots of especially short rods, and that means it's more likely that you pick a set of, on average, very large rods, on average, very, very small rods, and that means that these are quite spread out. Taking a sample, you can't be too accurate. But what you can control is the sample size. And what happens as n gets big, square root of n is still big, and if you divide by a big number, you get a small number. So let's just say you can't control sigma, but if you divide it by a big number, you get a small number. And what I'm saying is the standard deviation of the sample mean, so how spread out these are, is given by this number, and you can make that very, very small if you take a large sample size. Now, it might be difficult to take a large sample size. For example, with the concrete structure, you can't take out too many samples because that will damage the structure in the first place. So it becomes a difficult thing. And what happens then is you make your approximation of the measurement, but you have to say, look, I'm not certain about this. And later on we'll learn we're going to actually attach a number to how uncertain we are. But in general, what you can do, say with the rods, if you want, you can take a very, very large sample, say a sample of, say, 400 or something like that, and that might force this standard deviation. This is called a sample standard deviation. So let's take this. Well, actually, I can't even call it the sample standard deviation. It's a bit dangerous. So this is the standard deviation of the sample means. If you can force that to be small, that means that these are not spread out. They're all kind of similar. And so no matter what sample you do, they're all kind of the same. And remember, their average is the population mean. So if you can force this number to be small by picking a large sample, you're pretty much guaranteed that you're going to be very, very accurate, because these are all close together and their average is the population mean. And so basically pick any of them, you're going to be close to this. So that's a good situation. Unfortunately, you can't control how spread out the population is. Well, the only way you can do that is improve your process. And if you can improve your process, if you have a very high quality process, then you won't need a very, very large sample to be accurate about what is the average. Okay, so the standard deviation. So the thing about the standard deviation, you can't calculate it, because without knowing making measurements of all the possible rods, you can't actually calculate the standard deviation, but we can estimate it. You can look at the standard, and again we'll illustrate this in the next page. If you look at how spread out, if you do is take a sample of 10 rods and they're all kind of the same length, that's good evidence that the population standard deviation isn't that large. But if you've got like large rods, long rods, short rods, all in the same batch, that suggests that the population itself is spread out. And it turns out that the appropriate estimate of the population standard deviation, now we will be calculating standard deviation, so you've heard about it, we will be calculating it. So basically, the way to think of it is to measure the standard deviations. Look, I think we'll do an example on the next page. It's probably better than me explaining it here. But it turns out that if you want to estimate the population standard deviation, you can use what's called the sample standard deviation, which is a similar formula, except you divide by n minus 1. And we'll see this with an illustration of what I've been talking about. So suppose we use a sample of size 3 to estimate the population mean, which is 8, and standard deviation of this data. So the reason I picked such a small, like this is n equal to 5 and n equal to 3. If I make it any bigger, the number of samples gets too big. So let's see. So there are 5, choose 3, 10 possible 3 samples, these would be called. So 7, 10 of them. So how many ways can you pick 3 of these things? Here they are. And let's look at the averages. This one has an average 9.33, 9.33, 8.33, etc. This one gets it right exactly. And that's the only one. The other ones, so they're all supposed to approximate 8, but you can see some of them are better than others. So that's a good one, that's a good one, that's a good one, that's a good one. So the average of these is 8, which is exactly the same as the population mean. So if you average the sample means, you get the population mean. And remember, you sample, you take some of them to estimate the average of all of them. So we have that the sample mean is equal to the population mean on average. So now let's look at the standard deviations. So let us explain, say we'll do the standard deviation here. 7, 10, 11. So the average of these, certainly to 3 significant figures, add them up and divide by the number of numbers, is 9.33. So this sample mean is equal to 9.33. The way to think about the standard deviation is it's the average, it's the square root of the average deviation squared. Now what are the deviations? So the deviations are how far away the data points are from the mean. So the deviations are 2.33. I'm just going to write deviations here. I'm going to write this delta I. 10 is 0.66 away, and 11 is 1.6, or maybe 1.67, 1.67 away. So that's how far away 7 is from this average, 10 is, and 11 is. So what we do now with these deviations is we square them, and we get, and I'm just going to use 3 significant figures here. 2.33, that's 5.43. 0.67 squared is 0.449. And 1.67 squared is 2.79. So this is the standard deviation of these. Sorry, it's not. These are the deviation squared. And now what you do is you average these out. So I just write the bar for average. So 5.43 plus 0.449 plus 2.79, and I get 8.669. And what you do is you take the square root of that. Now I won't go into a big explainer of why. Oh man, it's not working. Oh yeah, okay. So the issue was, okay, we've got a problem here. I think I forgot to divide by 3. So 5.43 plus 0.449 plus 2.79 equals to this, divide by 3, square root of answer 1.699, which is 1.70. Finally, okay. So that's how you do standard deviation. You look at the deviations, how far are the numbers away from the mean, square them, add them up, find the average of those, and take the square root, and that's the standard deviation, right? So if we calculate the standard deviation of all of these 10 samples, so it's saying how spread out the samples are, we get these numbers. Okay, now the average of these, how spread out these are, is 1.94, but this turns out to underestimate how spread out this is. So we'll calculate the population standard deviation here. So the mean is 8. What is, now here's the 2.19, but let's calculate it. So the difference between these 5 and 8 is 3 squared, plus 7 and 8 is 1 squared, 7 and 8 is 1 squared, plus 10 gives the difference between them is 2 squared, plus 11 is 3 squared, divided by the number of numbers, which is 5, plus the average deviation squared, square root, you're going to get this 2.19. And that's the number that we can't actually find, because we don't, in the real world, we don't know all the numbers. It's just an illustration. So what we want to do is we want to, when we do a sample, we want to say how accurate it is. So we want to look at the how spread out these are, and these things, how spread out these are, is related to the population standard deviation. So we have to be able to estimate the population standard deviation. Now it turns out if you use the same formula to calculate the standard deviations of the samples, you get something that's too big. Look at that, 1.94. Sorry, too small. It's underestimating 2.19. The issue is, see this 7, 10, and 11, you're not calculating their deviation from 8, which is the average of all of them. You're calculating their deviation from 9.33, and they're biased towards this. So they might be spread out from 8, but they're not going to be as spread out from this. So you get this underestimation. So what we do instead is use what's called a sample standard deviation, where instead of dividing by the number of numbers in the sample, in this case 3, divide by 1 less. And what this does is it gives you a better estimator. Now it's not as good an estimator as the sample mean, because the sample mean is equal to the population mean on average. The sample standard deviation is not equal to the population standard deviation on average, but it's pretty good, and you can show there's no better one. So you end up with, if you do this, so instead of dividing by 3 as we did up here, divide by 2, you get these standard deviations, and the average of these is 2.37, which is a much better estimator. As it happens, there's no formula that does this very well, but this S with the n-1 rather than n is as good as we can do, and we kind of say that it's a good estimator, it's a good approximation, even though they aren't equal on average. Okay, so that's how you estimate how good your sample mean approximation is. You look at the sample standard deviation and divide by the square root of the number of samples. Okay. So if we do it here, for example, and this was our sample, we would say that would be estimated that how spread out these are would be the population standard deviation, which we can only estimate using this is 2.08, divided by square root of the sample size, which is 3. And this is the 3 significant figures, 1.20. So these are spread out to the tune of about 1.20. So what that means is, say when we get 9.33, we're expecting to be most of the time maybe like roughly 2/3 within 1.2 of the answer. So this one's a little bit more than that, a little bit more. This is within, this is within, this is within, this is kind of a little bit more. This is very close, this is very close, etc. Okay. And if you want to make this number as small as possible to make these all good approximators. Because of course you're only going to get to do one sample. So that's a lot of the theory. I think, in my opinion, you need to understand this. If you're going to structural, I have to be careful. I think you do more statistics if you're going to level 8. You definitely do if you're going to level 9. And if you're going to be a seriously good structural engineer, you will be working with statistics and you will have to understand a lot of this. Okay, so the sample means, these yolks, have what's called a T distribution. Now it's similar, I have no idea what I'm writing in here. It's similar to a Z curve, a normal bell curve, but slightly different. So the crack is here, I'm not sure what I'm going to put in here. So what we have is that T mu sigma over root n, n. So basically what it means, what happens actually is, as the sample size gets very, very big, the T distribution becomes a Z distribution, and we'll see that soon. Okay, I appreciate that probably doesn't mean anything at the moment. Okay, this variance might come up. This is just the square of the standard deviation. And a similar story, there is a table for the T's. Now the only thing I'll probably show you at this stage is down the bottom of this T, you see degrees of freedom. We'll have to talk, you see large, and this is essentially, they're actually Z numbers, which we'll get to eventually. I think maybe probably best to see this table in an example. Okay, so we'll keep with the theory here. Keep pushing the theory. So this is a graph. So if you were to look at in a bigger situation, apologies. If you were to look at a far bigger population than this, you have loads of sample means, and if you were to produce a histogram and make the histogram very, very fine, you get something like this. So for our one we looked at, most of them are kind of close to 8. Now there's only 10 samples here, I think, but if you do it, now there's a small chance you get very, very big and a small chance you get very, very small. And remember, the width of this at a certain level, and I mean a certain level is, I don't know exactly where to draw the width, is certainly here. This width is the standard deviation, population standard deviation divided by n. If you make n big, this peak will become very, very narrow, and that forces all your answers to be close to the population mean. But when that's not the case, there is a chance that you get large sample. So that's if you're kind of unlucky and pick larger than average things, and there's a chance you get a small sample. Okay, but the larger your sample size, the less likely that is to get it especially large, and the more spread out the population is, well, the harder this is. Okay, the most likely sample mean is equal to the population mean. The x bar and the x-axis are sample means, however, represented by the top and bottom tails are possible to choose. Okay, for example, suppose a sample of size n equal to 10 is taken from a population of standard deviation sigma, then 95% of the sample means lie within, okay, where are we getting this 2.262? So we're going to have to see this t table. So straight away, what I'm going to do is degrees of freedom here, which I don't really, it's kind of more technical statistical stuff. This is just n minus 1. Okay, so let's forget about just n minus 1. And we are going with n equal to 10, so n minus 1 equal to 9. Okay, and we want, okay, let's look at what we're looking at here. So here's the two tails, because what we want to do is we're looking for 95% of the sample means lying within two things. So here we want to get 95%. And so we're looking at a two-tailed T. So we're looking at the two tails, we're down here. Now, if there's 95% in the middle, how much in each of the tails? Well, 5% between them, so 2.5% here, 2.5% here. And so we're looking for 5% in the two tails. And if we go down from area in two tails equal to 5 down to 9, we get this 2.262. So T is also really a number of standard deviations. So T is equal to number of standard deviations, and the standard deviation here is equal to sigma over root n, and we approximate that, as we'll see in examples, at S over root n. Okay, so here we're seeing mu minus, so the appropriate t value here, as we said, was 2.262 minus that many standard deviations. And the average of the sample mean, remember, is mu plus that number of standard deviations here. So this can be also presented like this. So t is a number of standard deviation, depends on n minus 1 and a percentage p, the percentage p that are in the range. So now we can be 95% confident that our sample mean is between those two numbers, okay? But the thing is, we don't actually know the number mu. So we've got a different story. So I'm going to write down something here, and this is something that maybe you can think about and maybe understand, because I could spend a lot of time explaining this. I'll probably explain it once now quickly and maybe